Okay, so today we're going to be talking about how to solve angled launch problems for projectile motion. So after our post-lab discussion, or maybe you've watched the post-lab video for projectile motion, here are our equations if you are in one of my regular sections. And here are our equations for projectile motion if you're in my honors sections. Now again, these are pretty much the same thing. The only difference here is that I've decided to split up the delta x into an x final and x initial. And the same thing goes for my delta y for the y final and the y initial. So for regular, you'll see these as triangle x's. They essentially mean the same thing. So angled launch problems, there's a few more things that we have to remember, and knowing these things will give us more information when we solve our problems. Like horizontal problems, we have the x direction acceleration is 0 meters per second squared, and the acceleration in the y direction is negative 9.8 meters per second squared. For an angled launch problem, we now have a new bit of information for us where the velocity, the vertical velocity at the peak is 0 meters per second. That's because at the top, it has to pause for less than a split second because it's changing directions. At the peak is where it starts to go from traveling upwards and starts traveling downwards. So in order to make that change, it pauses for a very brief moment. There's also an additional part of the problem where we have to break down the initial velocity into components. So we have to mind our SOHCAHTOAs now and do a little trigonometry in order to even begin solving the problem. For symmetrical trajectories, so that means if the path of the ball is such that its initial and final heights are the same, we have a trick that we could do. So the total time that's in the air for is 2 times the time it takes to get to its maximum height. So if you think about it, this should hopefully make sense because a projectile travels in a parabola shape, and if its height initial and its height final is the same, then the path is a perfectly symmetrical parabola. So that means that, let's say it just takes 4 seconds to get to the top of the path. It's going to take 4 seconds to come back down. So that means it's in the air for a total of 8 seconds. And last but not least, we have to make sure we're organized when we list our givens. Alright, so the problem we're going to solve today is about a football player who kicks a football. The football has an initial velocity of 10 meters per second, and it travels 60 degrees above the horizontal. We have to determine the football's maximum height and also determine how far the football travels. So that's the x displacement, and we want the y displacement as it travels upwards. First things first, we need to break down this initial velocity into vector components. That way we can start working in our x and y directions. Now, from our forces unit, we should be pretty okay with our vectors. We know that the x component is horizontal. I'm going to call this v initial x. And after doing some SOHCAHTOA, which I'm going to skip ahead and do for you, we should get 5 meters per second as the horizontal component. Doing the same thing for the y direction, we find that our initial velocity in the y direction ends up being 8.66 meters per second. So the trig function that we should use there is sine of 60. Okay, so I'm going to start off by listing what we know so far. From the previous slide, we know that the initial velocities in the x and y directions are 5 meters per second for the x direction and 8.66 meters per second for the y direction. Additionally, we know that the velocity in the x direction does not change because the acceleration is 0 meters per second squared here. And we also know that at the top, so what we're gonna do is we're gonna cut this in half and only worry about the top. We know at the top, so first half, let's say, at the top our final velocity in the y direction is 0 meters per second. Its acceleration is negative 9.8 meters per second squared. And right now, we are interested in finding its vertical displacement. In honors, we'll say that it starts off at a height of 0, and we want the y final. So this ends up being pretty straightforward because we have that times missing here. So finding the height, we only really need to work in the y direction. The equation that's missing time is our v squared equation, so we're going to use the y version of that equation. V squared y is equal to 2a times delta y plus v initial y squared. Plugging in the things that we know, we have 0 is equal to 2 times negative 9.8 meters per second squared times change in y plus my initial velocity squared, which is 8.66. Now, solving for this, I'm going to fast forward a little bit, but after subtracting this to both sides, we get about 75 meters squared over second squared is equal to negative 4.9 meters per second squared times delta y. Dividing both sides by negative 4.9 meters per second squared, I have for delta y 15.3 meters. So that's the maximum height that the football reaches. All right, for the second part of the problem, we have to determine how far the football travels. So if we try to work with our equation for the x direction, again, we won't be able to continue because we don't have the time. So the only thing that we can do is go back to the y direction and work there to find some clues about the time. So what we can do is determine the time it takes to get to the top. So again, we'll be using this for the first half of the trajectory. This time I want the time. And since I have all of our variables filled out pretty much in the y direction, any of our equations will do. What I'm going to do is I'm going to use just the acceleration equation, the first one that we got in Unit 3. And it's going to be the y version of that. And I'm going to ask myself, all right, I know at the top it's at 0 meters per second. It's accelerating at negative 9.8 meters per second squared. That's multiplied by time, and it starts off with an initial velocity of 8.66 meters per second. All right, so this equation will tell us the time it takes to get to the very top. So once we do that, I find that the time is 0.88 seconds. Now, this is not the same time that we're going to use in the x direction. Now, the reason why, again, is because this is a symmetrical parabola. So if it takes 0.88 seconds to get to the top, it's going to take another 0.8 seconds to fall down. So multiplying that time by 2 gives us approximately 1.77 seconds for the time. So now we're able to continue, and I have my delta x, or my displacement or range, is 5 meters per second times 1.77 seconds. And this gives us 8.85 meters for my range, or my horizontal displacement. Okay, so that's an example of how you would do an angled launch problem. In regular physics, we pretty much won't get much harder than this. We will only do problems with perfectly symmetrical parabolas. However, in honors, we will do some harder problems, and then those we'll talk about in class. So I'll see you then.